All right, in this problem, oh my goodness, in this video, we're going to talk about inclined planes or ramp problems. So we're going to start off with you guys kind of doing some ranking on your own. So let's say we have frictionless surfaces, and we have these four situations where we have a block of the same mass on some different surfaces. So A is completely horizontal, D is completely vertical, and then B and C are at angles where C is a little bit steeper than B. So what I want you guys to do is to think about what is, or how could we rank the acceleration of these objects, and how could we rank the net force of these objects. So go ahead and pause the video, and go ahead and take like a minute or 30 seconds or so to do that. Okay. So hopefully you have some rankings down. You paused the videos, you did what I asked you to do. And your ranking for acceleration should look something like D. So I should probably say that I'm going from greatest to least, right? D, C, B, A. Okay. So A, because there's no net force, we can recognize that A has 0 acceleration. And D, well, D is just going to fall straight down, which means D is probably in free fall. So D likely has an acceleration equal to G. C has something a little bit less than G, and then B is something a little bit less. Okay. Now your net force ranking is likely going to look exactly the same because we have the same mass for each of these. Okay. Our net force is going to look like D, C, B, A. So then the question becomes, what's causing that net force? Why are these things accelerating, specifically B, C, and D? So you likely kind of have in your brain something about the force of gravity causing those things to either move down the inclines or move straight down. Okay. So what's causing that net force? Well, the force of gravity. Okay. Now, in B, the force of gravity, remember, is pulling straight down. So in B, only a little bit of gravity is going to pull us down the incline. In C, a little bit more of gravity pulls us down the incline. And then in D, gravity can put us right into free fall. So in all of these, it's the force of gravity that's causing us to accelerate down the incline or straight down. So that's going to play a role when we get into inclined planes. So with inclined planes, we normally have a situation like this, where we're on a nice flat surface. This is what we're used to, okay? And our coordinate system is X direction is horizontal, Y direction is vertical. Now, when we incline our surface, because that's what an inclined plane really is an inclined surface, our coordinate system is going to kind of tilt right along with it. So our coordinate system tilts right along with it. So we have still like this kind of up and down, but it's at a diagonal, and this side to side kind of at a diagonal. Now, we don't really want to call those directions X and Y because X is synonymous with horizontal, Y is synonymous with vertical. So when we're on an inclined plane, the directions that we deal with are parallel, meaning parallel to the incline. Right, and this system, that symbol there means parallel. And then we also deal with perpendicular to the incline. Right, so this direction is perpendicular to the incline because it makes a 90-degree angle with the incline. And then this is parallel to the incline because it's right in line with the incline. So when we are thinking about forces, we want to think about, are they in the perpendicular direction, the parallel direction, or maybe some combination? Okay. So here's a box on an incline, and we're going to say that this is a frictionless incline. So I'm going to write mu equals 0. So on this incline, or on this object, we have a force of gravity And then remember, we're on a surface, so we do have a normal force. And remember, normal force is always perpendicular to the surface. So perpendicular to the surface is along this dotted line. So my normal force needs to kind of point off at an angle like this. So if I think about that coordinate system that we just talked about, we have perpendicular to the incline, which is that yellow highlighted line, and then parallel to the incline, which is that green highlighted line. Oops, having some issues getting the pen I want. So again, that's perpendicular, that's parallel. So it looks like the normal force is nice and in our perpendicular direction. That's great. But the force of gravity is not perpendicular or parallel. It's a little bit of both. So what that means is we need to find components of the force of gravity, much like we would need to find components of any force that's at an angle relative to our coordinate system. All right, so let's say that our angle is theta. Okay. So through some geometry, which I am more than happy to show you, but this is a quick video, so I'm not going to show it now. What ends up happening is the angle that the force of gravity makes with that perpendicular direction, that also ends up being theta. So our angle that FG makes with the perpendicular direction is theta, the same as the angle of incline. So there's my FG, and that acts as the hypotenuse, and I'm kind of trying to draw it in the same direction as my free body diagram. So I have an FG perpendicular component and an FG parallel component, right? So instead of X and Y, we're using the directions parallel and perpendicular. So the perpendicular component pulls the box onto the incline, and then the parallel component pulls us down the incline. Okay. So back up here, when B and C were accelerating, it's actually the parallel component of gravity causing us to accelerate. Okay. So let's go ahead and figure out how we can find or generalize those components. So this is my angle here, which means FG parallel is the side opposite, and FG perpendicular is the adjacent. Right? Here's my 90-degree angle. So if I want to find FG perpendicular, it's the adjacent side, I need to use cosine. So FG perpendicular over FG. So FG perpendicular is FG cosine theta. So the weight times the cosine of the incline. Or if I don't have the weight, I would do the mg times the cosine of the incline. FG parallel is the opposite side, so I would use sine. Right? Sine is opposite, which is FG parallel over hypotenuse, FG. So my FG parallel is FG sine theta if I'm given the weight or the force of gravity on the object, or if I'm not, then I can calculate it by doing mg sine theta. So now that I know my components, I could redraw that free body diagram with an FG perpendicular pulling us into the incline, normal force pointing off of the incline, and an FG parallel pointing down the incline. Okay. From here, it's really not much different than what we have seen before. Right? We do net force equations, but instead of X and Y, we do parallel and perpendicular. So in that perpendicular direction, I have a net force of 0 because I'm not accelerating off the incline or crashing into it. So I have a normal force minus an FG perpendicular is 0. So my normal force equals FG perpendicular, which we just saw was FG cosine theta. Then in the parallel direction, that's the direction that I am accelerating, I have an FG parallel as the only force up or down the incline. So that's going to equal MA. So I have an FG sine theta equals ma. And if I substitute in for Fg with mg, I can actually get an equation for the acceleration, that the acceleration is based off of g sine theta. So let's see if this equation matches with what we know up here, right? So let's kind of assign some angles. Let's say this is 30, this is 60. So this incline would be at 90, and this incline would be at 0. So for A, if I plug in, right, A is that nice flat surface. Right? Well, I don't really have a parallel or perpendicular direction, but if I plug in the sine of 0, the sine of 0 is 0, so that gives me 0 acceleration, like we predicted. For B, right, where we're at 30 degrees, my acceleration is g sine 30, and the sine of 30 is a half, so a half g. At C, where I'm at 60 degrees, my acceleration is g sine 60, and the sine of 60 is 0.87. So this gives me 0.87 g. And then for D, where I'm that nice vertical 90 degrees, my acceleration is g sine 90. And the sine of 90 is 1, so my acceleration is g, like I predicted. So the equation that we're coming up with for the acceleration holds true with what we kind of see happening in real life. It makes physical sense. So that's an incline without any friction, just a force of gravity and a normal force. So now let's get into what if we are at rest, right? This is with friction. So we're going to do at rest, up and down, and then we're going to do some impacts of changing the angle, and then that'll be the end of this video. So with friction, if we are at rest, I have my force of gravity downward. Now, initially, this object wants to slide downward. So to prevent that sliding downward, the force of static friction has to act up the incline, and then I have a normal force. We talked before that the force of gravity is the thing that gets broken up into components. So we have an Fg perpendicular, a normal force, an Fg parallel, and a force of static friction. Okay. Now notice I still drew my initial free body diagram. That's like my official one. And then this is just the really helpful one. If I'm at rest, then the net force perpendicular and parallel are going to be 0. So perpendicularly, I have a normal force equal to Fg perpendicular. When I'm at rest, my Fg parallel has to equal my force of static friction. Now keep in mind, when we're calculating a force of static friction or calculating a maximum force of static friction, we do coefficient times the normal force. We're really used to the normal force being mg, but that's not the case here. The normal force is not equal to the force of gravity, but a component of the force of gravity. It's equal to Fg cosine theta. So the force of static friction, the maximum force of static friction here, would not be mu Fg like we're used to, but mu Fg cosine theta. And that's going to carry through with all of these. Okay. But for now, we don't know if we've reached the maximum. For now, the force of static friction would equal Fg sine theta. Because remember, the force of static friction only equals this part if we know we've reached the maximum and we're just about to slide. Up until then, the force of static friction equals whatever the applied force is, which in this case is that Fg sine theta. So now let's say we are accelerating, or we're moving up the incline. Okay. So I've given this box some initial push, so I have some initial velocity up the incline. So I still have a force of gravity and a normal force, and since I am moving up the incline, my force of friction has to point down the incline, and I'm now dealing with kinetic friction. So my free body diagram with components is going to look like Fg perpendicular, force of kinetic friction, Fg parallel, and a normal force. So net force perpendicular is pretty much always going to be 0 because we're not going to be accelerating into the incline or jumping off the incline. And unless there's some other like force applied at an angle, our normal force is going to equal Fg perpendicular. So that mg cosine theta. In the parallel direction, we are going to accelerate because looking at my free body diagram, I can see that there's definitely a net force because my force of kinetic friction and my Fg parallel add together. So I have mu times the normal force added to Fg sine theta equals ma, right? And we always calculate the coefficient of, the force of kinetic friction by doing this, right? If we know the coefficient and the normal force. So mu mg cosine theta plus mg sine theta equals ma. And as the flipping physics guy says, everybody brought a mass to the party. Every chunk of multiplication has a mass in it. So that means it goes away. So I have mu g cosine plus g sine. That gives me my acceleration. Okay. So we're accelerating down the incline. Okay. Now, what if we are going down the incline? What if we just let this thing go from rest? Okay. Well, if we're going down the incline, we of course have a force of gravity straight down, normal force coming off the incline, and since I'm moving down the incline, I have a force of friction up the incline. Perpendicular direction looks just like it has in prior questions. My normal force equals I should probably draw my component diagram, right? There's Fg perpendicular, Fn, Fg parallel heading down the incline. Fg parallel is always going to point down the incline. Just the force of friction that just might change, right, depending on the motion. And then parallel, big difference here. Instead of Fg parallel and the force of friction getting added together, they end up subtracting. So what that means is when we go up the incline, we have a larger net force, therefore a larger acceleration than when we go down the incline. So that's going to impact the distances traveled or the amount of time it takes to travel the same distance. Okay. So Fg parallel, mg sine theta, force of kinetic friction is going to be the exact same as it was for the last one. So we haven't changed the normal force at all. There's an m in every chunk of multiplication. So here we have g sine theta minus mu g cosine theta as our acceleration. So again, because we're subtracting, we have less net force here, so less acceleration, right? That less acceleration could mean more time to travel the same distance or more distance to have the same change in velocity, all things around that. Last thing we're going to talk about, like I said, is the impact of changing the angle. Right? So we're going to focus on increasing the angle. Opposites would be true if we decrease the angle. Okay. So we're going to say that this is a friction surface. Mu s and mu k both apply. Right? Maybe we're starting at rest and then sliding down an incline. So we got Fg, Fn, and since we're just going to let this thing go from rest, friction is going to point up the incline. And my component diagram, Fg perpendicular, Ff, and Fg parallel. Okay. So changing the angle is going to change a lot about this situation. And some things are going to be the same. First and foremost, let's talk about the things that are going to stay the same. Okay? The mass is going to stay the same, right? Mass of the object is going to stay the same. The overall force of gravity is going to stay the same because the force of gravity is just mg, not related to the angle. Some other things that are going to stay the same are the coefficients, because the only way to change these coefficients is to change the surface we're on. So since we're not all of a sudden lining the surface with sandpaper, those coefficients are going to stay the same. Okay, so the mass stays the same, force of gravity, coefficient for both stays the same. Okay. Where things change. Okay. So let's write out our net force statements, because that's going to help us figure out where things change. So my normal force and my FG perpendicular have to equal each other. So my normal force is equal to FG cosine theta. So let's see, I'm going to make two lists, increase, decrease. So the first things I'm coming across is FG perpendicular and also the normal force, which is equal to FG perpendicular. And the reason why these are the first things I'm coming across is because they're both based off of the cosine of the angle. So as the angle changes, the cosine is going to change. Now, for those of you in pre-calc, you know that a cosine graph looks something like this. The part that we care about is the part that goes from 0 to 90, which is this first chunk right here. Okay, so what that graph tells me is that as the value of the angle increases, which is the x-axis, the cosine of the angle decreases. So what that means is as the angle increases, anything that's multiplied by cosine theta is also going to decrease. So that means my FG perpendicular is going to decrease. And along with that, my normal force is going to decrease because my normal force is FG perpendicular. So then let's look at the x direction. All right, in the x direction, we have an MA, or we might be at rest if we're dealing with coefficient of friction, static friction. So we have an FG parallel minus a force of friction is MA. So FG parallel is FG sine theta, and friction is mu times the normal force, which is FG cosine theta. Okay. So I have two things based on an angle here, FG parallel and the force of friction. So for those of you, again, in pre-calc, maybe even algebra 2, you know that the sine curve looks something like that. And again, we only care about this part that goes from 0 to 90 degrees. So what that graph shows me is that the sine of an angle increases as the angle increases. So anything based off of sine is going to increase. So FG parallel is going to increase because it's based off the sine of the angle. Friction, on the other hand, is based off of cosine. Now again, this mu is the same, this FG is the same, but if this cosine is decreasing, like we've already discussed, then this whole entire term is decreasing. Force of friction, right? And that's going to be both kinetic and static forces of friction. Okay. So as we increase the angle of the incline, this object experiences less friction. So it's easier to get started moving, and then once it is moving, there's less friction preventing that motion. Okay, that's because the surfaces are not pressed together as much because the normal force has decreased because there's less of a component pulling the block into the incline. So now we should probably look at the net force overall, right? The net force. So we said that this FG sine theta is increasing and this force of friction is decreasing. So if I'm increasing this front number and then subtracting less of a number, that tells me that my overall net force is going to increase. And then similarly, we got to think about the acceleration, right? If my mass is remaining the same and I've increased my net force, then the acceleration is going to remain the same as well. So those are how increasing the angle is going to change all those different factors. Decreasing the angle would just do the opposite. So that's why I'm only covering increasing the angle. Okay. And that's kind of the basics of inclined planes. We'll do lots of practice in class.